shove the liquid oxygen or whatever the hell the fuel is in there and ignite it, and it works. It's like, wow, it's so simple.
A little more complicated than that.
That's like in a
But it
diagram,
seems so
it's simple.
simple.
Yeah, but in
You know,
reality,
the fuel's above it, and it just gravities into it, doesn't it? Just kind of like falls.
Well,
in the they got a pump
no.
going. I bet no one could guess what this is. In fact,
Shower drain.
Yeah,
Yeah. What do you think?
it does look like a shower drain.
It kind of does. It's
or
a
a
little
really
small,
like rain, shower.
Yeah. Well, you invented the thing. What is this?
This is the first Diana ever made.
Oh, yeah.
Kind of.
Yeah. What kind of the shape?
Well, it's a square,
Yeah.
in case you can't tell. This was mainly designed to test the cycle time in the machine to drill these holes, and as a bit of a discovery to see in practice how feasible is it to machine something like this and how close they could be while having a rigid enough assembly that it doesn't cause issues and fatigue and stress and stuff like that, failures.
Yeah, I mean, people probably don't realize, but there was a complete evolutionary process in designing from the first Diana to current gen. It's never really ended. The evolution has always continued, and it started with a simple, row column. I don't know how many holes are in there. Probably 600, 700. I don't know.
No, 300, 250 or something. I don't know.
Oh, these are bigger holes.
People could count on the internet.
Yeah, but bottom line is this is where it starts. Is you have an idea, and I mean, it would be difficult probably to 3D print something like that with all those holes to make it. It wouldn't come out too clean, would it?
No.
Yeah, not enough resolution.
The point of this is just to see the cycle time on a part like this, which there's more in it than people would think, because the machine has to locate on each hole. It needs to move up and over locate before it plunges. So it's more than just the physical drilling. And in fact, on the machine we were running this on, around 2/3 of the time to drill these holes was just physically the machine getting in the right spot before it plunged.
Oh, that was the Mazak we had then, the big Mazak?
Yeah, so it's a big 40
Yeah.
taper
It's a lot
machine. It's a big
slower.
heavy
Yeah, it
machine.
had a lot of moving mass.
Right.
Yeah.
And it's a little different comparing like a simulation to something like this. So I guess what we want to get across is the hows and the whys behind the designs, the things that changed over time.
Yeah.
Because there's a lot.
Right, yeah.
And I guess it's sort of behind the scenes.
It began with a concept. Like, we had
Right.
we had our driver. We knew the size of it. So it's like, now we want to make a compact headphone. What do we put that in? How do we fit it into a shape that is aesthetically pleasing? It can go on your head, bubble. There's all kinds of factors you had to look at, right? But this was the beginning.
Yeah, we had criteria.
Yeah.
We said it needs to be very similar to driver to what we were putting at the time into 1266. But we want it to be thin, lightweight, very rugged, and like a traditional headphone in fit and appearance and things like that.
Yeah, in fact, one of the main goals was thin it out as much as possible. As much as possible.
But that also means why we couldn't really 3D print it, because we needed to know how thin you can make it in the material it's going to be made of, and how strong it would actually be. Because if you made it out of plastic, well, that doesn't really tell you anything, right?
Yeah,
And we do it for the form, but not for the strength.
And we also found that sonics vary too. If you run plastic versus metal, the back wave or the bounce off that, it sounds different. So you can't even properly finish tuning a headphone without having the materials to use to do it.
It's actually an issue because this is actually honestly quite difficult to do. If you're talking about prototyping, one example like this is non-trivial. Like you can see, this doesn't even actually have any inner geometry. This is purely a functional prototype just to show more or less the strength, the feel, and stuff like that, and get an idea of what it looks like in the hand. You could look at a simulation, and you could make all kinds of models and things like that to kind of triangulate on what you want. It's so very different when you're actually holding it in the hand. You put a coat of paint or some sort of finish or anodizing process on it. When you're feeling the product fully assembled, oftentimes it's so far off from what you expected from the computer screen.
Yeah, you could change the hole pattern or the way the machine's drilling the holes or the size of the holes, and it changes the edge geometry of the hole and how it cleans up when you're prepping it for finishing and stuff. And what steps you got to make in the process in order for it to come out as a finished part and feel smooth. And yeah, it's crazy when you look at it. So you that's the problem with making changes too, right? You make one change and it can affect 10 other things. Now, all of a sudden you got to change your procedures and how you prep it, finish it, assemble it.
Well, yeah,
all kinds of things can change.
I remember, you look at the 3D model, but that doesn't tell you how you're going to make it, right? Because I remember the biggest problem was like to machine all these holes, you had to machine it while it was still black because you run into problems if you did it afterwards. Then there'd be so much deflection on this that all the holes would come out all wonky.
Yeah,
so you got to figure out the order of operations to manufacture it.
Yeah, because in the process of this, we're trying to make the parts as light as possible because you want to minimize the weight of the headphone. So you're removing as much material as, how would it go? You're removing just as much material as you can, but no more.
Yeah, you're figuring out
like that.
what you can get away with.
Right.
And that's where physically making it and iterating comes into play. And that's honestly essential. Because of course you could design this in a computer and you could know it would work. The way you do that is you build confidence in the design, typically by overbuilding. Or if you have direct experience in something similar enough or extensive experience, it's possible you could get pretty close. But inevitably, if you want to know that it's as thin, as light as possible, while also meeting all the design criteria and being strong, you got to make it. Because then you also occasionally run into issues when you're making it where something doesn't work the way you expect, or it takes longer than you expect, or there's issues.
Yeah, and to build on that, I mean, I think the first Diana we did, the original Diana, was probably heavier in terms of the thickness of the metal.
Oh, yeah.
Right.
And we were concerned about if someone could actually squeeze it somehow enough to bend the metal in and stuff like that. So we made it up to be a tank. And then once that was out in the field for a while and we saw that people couldn't hurt it, we started to get a little more you started to get a little more creative on the machine process. You remove more material to lighten the weight on the next generation, right?
Right.
And and again, that's been out in the field for a while. We saw that people couldn't damage that at all, and so we continue to evolve the design, the whole pattern. And now we've the Diana TC's it's still way more refined than the other models.
Yep.
Right? I mean, you think about the changes you've made.
There's a lot.
That's got to be thousands.
I sort of want to go through them, but it's like...
Yeah, right.
It's exhausting.
Just play the machine code right here on the, right in the back screen of the machine running the code. You know what I mean? It's just nuts how many steps there are to make the inside of one of these to shape it.
I mean, it's a lot more work to make a one-off machined prototype like that. But there is another advantage it has over seeing a model or 3D printing it is in the real world when you're making it, the tolerances you could actually hold. Because when you start talking about multiple pieces that need to fit together, you need to be able to practically make it and have it actually fit together reliably.
Yeah.
So, I mean, you got practical limitations. You could design something in a computer that you actually can't manufacture, Yeah. So that's a whole different thing.
Or it's a real bitch to assemble.
Well, yeah, that too.
That's why we found that bringing the manufacturing in a little closer with the design and whatnot is so incredibly important. It's the more expensive and more difficult way to do it.
Yeah, it's a huge upfront investment.
However, what it enables is you could run a part close to what you expect to make. And you could say, what problems did we have manufacturing it? What are the cycle times? You could predict cost of manufacturing, and you could hopefully make iterative changes to design out the problems and take material away where it isn't necessary. You could say, in service, in our uses, in our simulations, we predicted we would need more strength here than we needed. We could pull that away and try it and test and iterate and make sure that we don't have deflection issues that's causing issues to meet tolerances, and we could see what we actually achieved in production. And you could more or less design around these tolerances. Whereas instead of guessing, well, maybe we could hold 5 thou, maybe we could hold 2 thou, it was easy to hold this spec. So maybe you could push the tolerances tighter than you would otherwise. And if you're farming it out, you're kind of guessing, and you're always going to be more conservative, because if you're not, it means a mistake and you got to redo it and a lot of costs. Whereas doing it yourself, there's still costs, of course, but they tend to be a lot lower than farming it out. And on top of that, you get the experience when you're making it.
Well, that and the finished product is exactly the way you want it versus good enough, because when you're paying someone else to do it, at some point, it's good enough. You can't just keep paying people to do the same thing over and over again just for minor refinements. You know what I mean?
Yes.
Yeah. Where here it's continuous refinement. It's just there's always stuff being thrown into this that becomes the next model. And a lot of people they like the AB 1266 comes to mind because it's been around the longest, right? 10 years ago, it's 10th anniversary. We talked about that, and that design, original design. If you look at the chunkiness or clunkiness of the machine process, the original ones, compared to today's, how smooth the corners are and the edges and the fine detail and the little American flag machined into the inside, and there's all this extra detail in the design that just didn't exist at the beginning because we didn't know how to do it, and and you were just worried about making at that time we were just making about finishing,
work.
the design, the main design.
Yeah.
But now all the artistic flair that you've been able to add over the years into that, and even the finishing process where we go from an anodized aluminum to now a Cerakote or a polymer ceramic finish, with a multi-tone process and all the steps involved. I mean, it's crazy when you think about the evolution of just that headphone in the last 10 years. But when people look at it, like on a photo on somewhere, they're like, oh yeah, but no, it's not completely. If you had them in front of you, you could see the quality in the new designs relative to the old. It's just night and day, and it's all baked in. It's baked in with a shit ton of time on your part and everyone's part to get the finishing right, the machining right, just really refine the process, the assembly procedures.
I mean, the biggest thing, thinking back though, was not being in control of the anodizing, and we'd get them back and they wouldn't match. And then we didn't have any parts because all of them don't match, right? Yeah. So we were like, well, we can't ship anything for another 2 weeks because we need to ship them out to get re-anodized or whatever.
Yeah, imagine like matching shades of black, right? And that's what it is with an anodizing process, right?
Yeah,
you get a batch done and they look black, and then you compare them to an old batch that was done in a different black.
Right.
It's like trying to match white. If anyone's ever tried to match whites, it's
Same
even
thing,
worse.
Yeah. There's 10 million different shades.
It's crazy. There's bright white. There's white. There's white is not white.
That basically is just a design issue. That's not, anodizing is not the right choice for 1266 because of how many metal interfaces there are that are very, very difficult to get right.
Well, we learned that all of it had to be done in the same batch.
Right.
All parts had to go out at the same time, done by the same guy out at the plating place at the same batch.
Right.
Otherwise, you're screwed.
Right. Which in the early days never happened because it's like, we were happy to get whatever we could out when it was done.
Yeah, the machining process is so slow. It's like we're kind of like, it's more of a serial manufacturing process where now it's more parallel.
When we started designing that thing, we figured we wouldn't sell many units. We figured it'd be very low volume, so that wasn't an issue.
Right.
It was designed to be in small batches. And that's sort of the issue. Those are the changes that happen over time. It's all this nuance, all the data that you get from now that you're actually manufacturing it, from running it, figuring out the problems and whatnot, what changed from your expectations, and now customer feedback, and whether or not the number of units you're shipping changed. All this data kind of gets roped together, and you hope to evolve and iterate the design. And a lot of times, this is rolled into the same exact product with time. You continue to evolve and improve the product. And it's curious because a lot of times consumers are somewhat unaware of this. They assume, well, it's this product. It's the same thing as it was years ago. And with some manufacturers, that's true because they don't do the manufacturing. They're not aware of the issues. So they don't change anything because to them, they're blissful. Right? Everything's working fine. They don't know the issues. But there's a lot of things you could do to improve the product, make it more durable, reliable, fix issues, and things like that when you have that experience. And we've been sort of on that path all along, with 1266 and Diana.
It's called hindsight, and there's no way around getting it. There's no shortcut to that. It's
unfortunately.
Unfortunately. You got to be really, 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 really good in your art to not require it.
Well, I guess
so. Isn't that the chicken and egg concept? You have to have hindsight in order to know the mistakes that are going to happen, so that you could design them out of that whatever the design is you're creating. And
it's kind of like a college student that just graduated with like an engineering degree, right? You have the knowledge, but you never actually made anything, right? So obviously you're not going to just come out of college and be like the best, at whatever.
Well, you haven't interfaced with other vendors and understand their limitations and what can actually be made when it's all in a book on paper.
Right.
It's black and white.
World,
yeah, it's perfect. We did that video where nothing's perfect.
Right.
You in school you live in a perfect world. You don't think about the imperfections that are going to occur when you go out in the real world and try to make it.
And more importantly, there's incredible nuance involved with getting things made. A lot of times you don't learn as an engineer anything to do with cost. And maybe more civil engineer, you'd be more aware of that. But a lot of times other engineers, cost isn't as big of a concern. It's more about getting the process done and getting the thing to work or whatever. And in the reality, you tend to run into cost as being oftentimes your number one factor. You could make something out of an exotic material, but is it 10% more or is it 5,000%? It's a big difference, right, to the consumer.
Especially on a complex design.
And then beyond that, let's say you could afford this exotic material. You go to a vendor, you say, I need this part with impossible tolerances in this very difficult, expensive material. They're most likely going to laugh at you because you don't have the volume for them to tool up to figure that one out. Because they know it's hundreds, if not thousands of hours to get that part made. And they could quote you $7 million to make 50 pieces, but they know you're just gonna laugh.
It's too bad you didn't tick off like a clock timer over the years of how much time you've spent refining just this one design. Yeah. And, it's funny when you think about it though. Like there are many other manufacturers that make products who will just shit can a design. Like every model is completely different than the last, which is kind of pretty common, really.
It is.
And so to me, you never get a chance to refine.
Yeah, like the end, like the best this could be.
Yeah, it's like if everyone's different, then everyone's different. You never really hone in on what you could really do with that one design. And I mean, it's a different way of approaching this. I think because we're in a subjective thing of audio where people are actually listening to this, the end result is, how close to the music can you get with this one thing, right? And then what changes can we do to get you closer to it? And to shit can a design and start over from scratch, you're starting that process all over again to me, really. And it's hard to do. It'd be very difficult to optimize anything, to really hone in on it if you're always making something different,
The thing that always gets me is a lot of times I could see people seeing something like this, hearing about this interaction we're talking about here, and saying, well, it's just because you don't have the experience, because you don't know. And that's true to an extent.
By the time we did it.
However, even companies with tens of thousands of employees, the best in the world, Apple and Tesla, everyone, right? They have some of the best employees out there. They have an incredible lifetimes of an experience. They get it wrong, right? Publicly facing, sometimes they tell you about a thing that ends up changing or ends up occasionally even not happening or ends up being a very optimistic timeline. And these are people that know better.
Yeah, you got hundreds of sets of eyes. You got hundreds of sets of eyes on a design,
right?
Prototyping, finished product.
Well, that's a different problem.
And they still miss it.
So clearly, it's obviously very, very difficult.
Well, just having a bunch of engineers working together is a miracle in of itself.
That's probably where most of the mistakes come.
Yeah.
One hand doesn't know what the other's doing, and or miss something in the translation. And when these parts all come together, they don't. It's like, oh.
Yeah. Well, yeah, if it's just you, and you, well, at least you know everything about this product because you're the only one working on it, right?
Yeah. I mean, you could just see the complexity of it. And I mean, we do because we've done it. And, that's kind of what separates the manufacturer, even though I don't need to go there too deeply, but the manufacturer from the consumer or the reviewer, the guy looking at it and judging it by its appearance. Like when we first tore apart, when back in the days, someone handed us the first over-ear Apple, whatever they call it, right?
AirPods Max.
Yeah, right. And Douglas handed us this and that, and it was one of our most popular videos, and we're just sitting there staring at it going, oh, look at how they made the ear pads and stuff. And people thought it was cool how we didn't rip it apart, but we just, we were just describing what we saw as designers, what they did to this, and it's a whole different way of looking at it. We look at things a completely different way, which is another video we did.
Yeah.
But it's true, we do. And I think what would really be helpful here is the reason we do these videos is so that the consumer and the reviewers and everyone else do understand that there's a process that's involved with this, that we sort of know what we're doing here. I mean, we kind of worked at this a long time, and the end result is as good as we could do at the time. And it is what it is. That's it, And I mean, it's there's limitations to everything. You can only take it so far because you run out of time. At some point, time is a factor. You got it. At some point, you actually got to sell something. You got to say, okay, that's as good as we could do right now, unless we spend another 3 years doing this. So to me, the way to get around this is put the product's good. It's field. We tested in the field. It works. We know it's going to hold up, right? We go through the whole process. And when you feel comfortable enough to put it out there, you put it out there, right?
I don't see any other approach. And it sort of sounds negative to some extent.
I know, in some ways. I'm hearing myself and I'm like, well, I don't know any way to describe it, but that's the way it works.
But that's the reality, and everyone does it.
Yeah.
Because if you actually have high standards for a product, if you want to deliver a product that's spectacular, the best in the world, best in the industry, it is nearly impossible to do that without having customer feedback. And those are the realities. Engineers always know best, so they think, right?
I think the most...
And they don't know how the consumer is going to use it.
Since we always bring up Tesla and all that, I think the most obvious thing, I think, that how this works is watching them try to make a rocket land itself. And everyone saw that on TV because they showed the mistakes. They showed the rockets crashing into a ball of fire every time until one finally just about
Basically,
stood
yeah.
up and tipped over, right? And you see the evolution of that process.
Which is unusual in that industry.
You know, yeah.
Normally you just see it when it's done.
Yeah,
it's
right.
all secret.
Yeah, they showed the entire process.
The profound thing here, though, that I think a lot of people miss out on, SpaceX tends to be consistently rated the number one place that engineers want to work. So the top brightest engineers in the world,
I can see why.
they want to go to SpaceX.
Apple was like that,
oftentimes, Apple's very high on that list as well. So they have some of the best, most talented people in the world working as hard as they can. This is their life's mission to get these things to work, right? It's not a job. This is what they care about. This is what they like, right? They're thinking about it all day, every day. Yeah. And they tried as hard as they can to get this rocket to work properly, to land, to work, and it didn't.
Many times.
Does that mean they're idiots? Does that mean they don't know what they're doing?
Yeah,
right. It's just something nobody's ever
We're
done
talking
before.
thousands of people coming together to make this happen.
It's incredibly difficult, obviously.
Not one or two.
And a lot of money.
Yeah. And the curious thing is you always see people, you saw so many people saying, oh, that's foolish. That's not possible. It's not going to happen. And they tried it and they failed and they tried it, they failed. And eventually they got it to work and people are like, oh, okay, and they sort of changed their tune, but not really. And now nobody says anything because it works so reliably.
Yeah, right.
They don't explode every time they land. They land pretty reliably. And that's what confidence is, right? From an engineering perspective. Now you know, we did this, we went through the process, you have the scars from understanding how this process went down. What you discovered along the way is hyper critically important.
Oh yeah.
And now you know how to make it work.
You take that
and you take that
forward,
with you,
right?
It makes you a better engineer, makes you a better designer.
Well, from our perspective, it's the same. I see what NASA was getting at because they were telling them they wanted to keep refining. And NASA's like, stop. Yeah. You have to stop. It works. And if you want to actually put people on these, you have to stop changing everything and show us that the design is good enough where you could just keep making it like that.
Right.
And they I'm sure the people at SpaceX didn't like that.
Oh, it's probably
stop
terrible.
refining it, but
you want us to make the next 8
point.
rockets the same, but we know improvements now. We could fix this.
Right. But they had to. Because NASA said you have to.
The priorities shifted then from R&D to
actual production.
Yeah, right. And it's like, and then the mistakes that go along with that, that you learn along the way, that you go back and tweak to fix them. So, can you imagine the evolution process of a rocket like that?
Well, a little bit more complicated.
Yeah, I mean, it's just nuts when you look at the component count and things like that, and how those engines are something, and they simplified them too. You look at like the old engines and the old rockets. Jesus, it's like a plumbing nightmare when you look at how that. It's amazing the damn thing didn't blow up on the pad, which they probably did. Yeah, but you look at how they simplified the design. You know, it reminds me that looking at today's designs. It reminds me. I remember years ago when I was looking at a new furnace for the house, and they had the Lennox Pulse, and it was like a chamber that they built with this, like basically, I don't know if it had like spark plugs in it.
Yeah.
And it would throw shots of gas in there like an injection and spark at the right time at like 60 cycle rate. So this thing hummed when it ran, and it produced an explosion rather than a constant flame, right? And the guy salesman was trying to push on us because it was new, and I'm thinking to myself, well, first of all, I'm very sensitive to 60 cycle hum. So I'm not going to sit here listening to my furnace going, while that's running, right? Because you got to believe it's going to make a noise. It's exploding 60 times a second. But anyway, think about, that's what reminds me of these rockets. They've gotten it down to like a chamber, and they just shove the liquid oxygen or whatever the hell the fuel is in there, and ignite it, and it works. It's like, wow, it's so simple.
A little more complicated than that.
That's like in a diagram, it's simple. Yeah, but in reality,
the fuel's above it, and it just gravities into it, doesn't it? Just kind of like falls. They got a pump going.
Yeah.
No, they're very complicated. So it's basically that's sort of like this, like anything really. You look at something, you're like, oh, it's a part, it's a piece of plastic, it's a piece of metal, and that's all you think about it as a consumer. But you don't see the vast amount of time and effort that went into making that part the way it is.
No doubt.
And that's sort of the thing that's kind of hard to really grasp. The part you see is the one that works. There's oftentimes a lot that didn't, even though the person or the people, the group of people going into it with the best of intention and all this education, they thought they were going to get it right, and they didn't.
Yeah. And you're only seeing like the cover of the book. So, as the saying goes, it's don't judge a book by its cover, right? That's all you see when you look at a finished product is you don't see the interior. You don't see any of those tens of thousands of man hours that went into getting this the way it is, just the way it is, and And so anyway, it's been a cool process the last 10 years when you think about 15 when you count the R&D before we even started making a 1266.
It's not like the product didn't just appear one day.
Right. Yeah, that'd be nice.
Selling it. Yeah.
3D print. Now you could just 3D print a 1266.
But kinda. But that is true because if you think back,
that would be bad.
At least like SpaceX these days, they had computers and all the modern stuff. Back in like Apollo, everybody was like paper and slide rules. Now that was some real stuff.
To me, that just blows my mind. I mean, those guys were good. I mean,
hard.
Those guys were really good.
Yeah.
Really good to be able to put people on the moon and bring them back.
I almost want to do a video on this.
Never have done it before, right? But I mean, they did throw shit in orbit, but
it was a lot of testing.
Yeah. In fact, didn't even a flight go there and back without getting? They did go through that.
A lot of testing.
And a lot of money.
Yeah, right. Oh, that's true. Yeah, they spent a lot of money really quickly. A lot of money.
Because even then, NASA was at their peak, we'll call it in the 60s or so, and they had practically unlimited budget. Top engineers in the world.
The government's like
going at it.
I don't care what it costs, do it.
Right.
Wow. And they were doing everything they thought as aggressively as they thought they could because it was a race, right? And they still said, we need to stop here and test all these elements together. And we need to stop and test all these elements. Because obviously they tested all the pieces.
You can't speed the process.
And then they put it all together. They did testing, because they know sometimes you put it all together, something fails. And then if it blows up, it's very hard to know why.
Yep.
And unfortunately, that's the reality. You just have to make it, try and see, even if you're the best of the best. Maybe one day we'll know better and we'll be able to figure these things out.
This is the process. This is the design process. Yeah. It is what it is, and you can't fault it because the more of that you do, ultimately, hopefully, the better the product comes. The final product is right, and vice versa. The less of it you do,
right?
So I mean, you put the time in, and it tends to show. It usually shows. I mean, if it doesn't, then you're doing something wrong.
Or you give up.
Yeah, you shit can that, and so the tangent went the wrong way. But I think we covered that well enough today, and thoroughly bored most people.
Yeah, that's a good primer into the topic.
Yeah.
It's pretty, honestly, very exhaustive to really consider.
Yeah, this 20-minute talk
is
covering 10 years of time to get to where we are to be able to talk about it. You think about it, 15 years or whatever.
I think you'd be hard-pressed to find someone that actually designs stuff that won't tell you that they may not get it right perfectly the first time.
Or second or third, really.
Right.
Yeah. But every time it's a little righter.
Hopefully.
Yeah. On that note, everyone, subscribe. We're always got new stuff coming. And if you click subscribe, then you'll be pre-warned. Or is it warned the right way? Yeah. You'll know about it.
You'll be made
aware.
You'll know
what's coming next. Thanks, everyone. Take care.